In previous videos, we've learned how to factor expressions that took the form x squared plus bx, where b was just some number, plus c, where c was the constant. So for example, x squared subtract 7x subtract 12, for example. We've learned how to factor expressions that look like that. But not all expressions, not all quadratic expressions take that form, and so we're going to look at some examples of other forms of quadratic expressions that we can factor. Now the first form that we want to look at, or that I want to look at, is called the difference of squares pattern. Difference of squares. And so in the difference of squares pattern, we are looking for expressions that take the form a squared subtract b squared. And when we find an expression that takes that form, then we can replace it with the factored expression a plus b times a subtract b. Now let me show you an example. Let's say I have the expression x squared subtract 9. Now this may not seem like it's in this form. For example, I don't have an exponent on the 9 here, but I can rewrite this expression so that it is in this form of a squared subtract b squared. And so if I rewrite this as x squared subtract 3 squared, remember 3 squared is the same as 9, so I haven't changed it at all. This is still an equivalent expression, but now it's in this form where I have some quantity squared subtract another quantity squared, and for this, once I've manipulated it, my a value is going to be x, and my b value is going to be 3. And so with that in mind, I can rewrite this expression as x plus 3 times x subtract 3. And so that I just use the difference of square pattern to factor out x squared subtract 9 into x plus 3 times x subtract 3. Now, as just a side note about why this works, the reason that this works is because we can also imagine x squared subtract 9 as equivalent to x squared plus 0x subtract 9. So this is an equivalent expression here because this middle term is equal to 0, so we haven't added anything into it, but we've put it back into a form that we might be more familiar with. Now, what are two numbers that multiply together to make -9? Well, 3 and -3 multiply together to make -9, and those two numbers also add together. 3 plus -3, that adds together to make 0. And so similarly, I can rewrite this expression as x plus 3 times x minus 3, or x subtract 3. So this is just the difference of square pattern is just a little shortcut that we can use. Let's look at another couple examples. Let's say we have x squared subtract 49. Now 49, just like 9, is a perfect square, which means that it's the product of a number multiplied by itself, and so that number is 7. So I can rewrite this as x squared subtract 7 squared. Now here my a value is x again, and my b value is 7. And so I can rewrite this or factor this as x plus 7 multiplied by x subtract 7. Let's do one more. Let's say I have x squared subtract 36. 36, just like 49 and just like 9, is a perfect square, which means it's the product of a number multiplied by itself, and that number is 6. So x squared subtract 6 squared. Again, I've just rewritten this expression into an equivalent expression with 6 squared instead of 36. And now my a value is going to be x, and my b value is going to be 6. And so I can take that and rewrite x squared subtract 36 as x plus 6 multiplied by x subtract 6. So again, I've just used the difference of squares pattern in order to factor x squared subtract 36 into x plus 6 times x subtract 6. That's the difference of squares pattern. The next thing that I want to look at is not so much a pattern, but a situation that comes up a lot when we're factoring quadratics, and that's when we have a leading coefficient that's not 1. Leading coefficient that is not equal to 1. So remember, if we had a leading coefficient that was equal to 1, then it would look like this. We'd have x squared, like the example I had before, I think it was x squared subtract 7x subtract 12. So this has a leading coefficient of 1. We don't write it because it's implied, but this has a leading coefficient of 1. If you wrote it like this, it would obviously be the same thing. 1x squared subtract 7x subtract 12. So we're talking about scenarios where the leading coefficient is not 1. And so let's look at one of those examples. So let's say I have negative 6x squared subtract 13x subtract 6. So negative 6x squared subtract 13x subtract 6. And I want to factor this into factors, and so the way that I'm going to do that is I'm going to follow a similar process for when we have 1 as our coefficient or as our leading coefficient, but it's just a little bit more involved, and so let's walk through it. And just to review here, the leading coefficient here is negative 6, so it's not 1, and that's why we're going to follow this particular process. So I'm going to start by taking my leading term, which is there, and my constant term, which is here. I'm going to multiply those two terms together. So negative 6x squared times negative 6 is going to multiply together to 36x squared, because negative 6 times negative 6 is positive 36, and then we have x squared multiplied by that. And then I'm going to write this little line that make this little t. Now underneath this 36x squared, I want to write two factors that multiply together to make 36x squared, and then add together to make negative 13x. Let's see, if we have negative 9x times negative 4x, let's try that. So negative 9x times negative 4x. So if I multiply these together, it's going to be negative 9 times negative 4. Negative times a negative is a positive. And then we have two x's, so that's x squared. So negative 9x times negative 4x makes 36x squared. And then if I add these two together, negative 9x subtract 4x, that's going to give me negative 13x. Now what I want to do is take negative 9x and negative 4x and combine it back with these two terms that are underlined here. So let me show you what I mean by that. I'm going to rewrite this expression here as negative 6x squared subtract 9x. And then I'm going to put this in parentheses, and then we're adding to these parentheses, to what's contained in these parentheses, we're adding negative 4x subtract 6. Now the next thing that I want to do is I want to factor out a factor such from each of these each sets of parentheses here, such that what's left inside the parentheses is the same for both sets. So let me show you what I mean. If I factor out a negative 3x from this set, then that's going to leave me with 2x plus 3. And I can double check that I've done this right by just distributing the negative 3x back over what's inside the parentheses. So like negative 3x times 2x, that makes negative 6x squared. And then negative 3x times 3 gives us 9x, so I've done that correctly. And then the next thing that I want to do is I want to factor out something from here such that what's left inside is equal to 2x plus 3. So if I factor out a negative 2, then what's left inside is 2x plus 3. So I've just pulled a negative 2 out of these parentheses, and I can double check that I've done this correctly by imagining if I multiplied this negative 2, or rather if I distributed this negative 2 back over what's inside the parentheses, then I would have negative 4x subtract 6. And so now that I have that, I can do one further factoring step, where here I have negative 3x times 2x plus 3 in parentheses, and then subtract 2 times 2x plus 3 also in parentheses. So I can factor out a 2x plus 3 from this expression here, and when I do that, it will look like this. I'm factoring out the 2x plus 3, and so I have 2x plus 3. I factored that out, and what's left are the negative 3x and the negative 2 here. So negative 3x subtract 2. And this, I'll put a box around it here, this is the factored form of the expression that we started with. Let's do another one of these. It looks similar, but it will the result will be different. So let's say we have 6x squared. 6x squared subtract 13x subtract 5. So I want to follow the same process here, where I take my leading term and my constant term and I multiply them together. So 6x squared times negative 5 makes negative 30x squared. And then I'm going to write this little t structure. Now in this t structure, I want to write the factors that multiply together to make negative 30x squared and then add together to make negative 13x. So just like we've done before, you could write out a table of the factors of negative 30, but you'll eventually find that the two numbers that work are 2x and negative 15x. So 2x times negative 15x is going to give you negative 30x squared. And then if you add 2x and negative 15x, that's going to give you negative 13x. Now I can rewrite this expression here using what we found multiplies together to make negative 30x squared. And that's going to be 6x squared plus 2x. And I'm going to put that in parentheses, and then I'm going to add to that negative 15x and negative 5. And so just like we did over here, I want to find something that I can factor out of both of these sets of parentheses such that what's left inside both sets is the same. And so looking at this, if I factor out, looks like I can factor out a 2x from this set. So that will be 2x times 3x plus 1. And then if I factor out a, let's see, negative 5, if I factor out a negative 5, then that's going to leave inside a 3x plus 1. So again, I have the same values inside of these parentheses. I've factored out a 2x, and I've factored out a negative 5. And now I can factor the 3x plus 1 out of this entire expression to be, so that it becomes 3x plus 1 times 2x subtract 5. And that is the factored form of this expression here. And if we wanted to check our work on either of these, then we could use each by each or FOIL and distribute out to double check that we got back to where we began.